Awesome. All right. So you're all Infiniscope members in this room today, but maybe you haven't engaged with us for a while, and that's a-okay. Just a quick reminder, we do have classroom-ready content, so interactive, adaptive digital lessons on our website that you can launch directly from there. We also have the ability to enroll students, so if you want to capture data, you can do that as well. We also have Tourit, our virtual field trip creator. So this is great for place-based education, getting students out into the field without actually getting them out into the field, still getting some of those benefits. And then we also have our simplified lesson builder that allows you to build your own adaptive lessons with real-time feedback. All very, very cool. And without further ado, our speaker today is Dr. Nat Mathews, who is a postdoctoral fellow at NASA Goddard Space Flight Center. Dr. Mathews holds a Bachelor of Science in Computational Mathematics from the Rochester Institute of Technology and a PhD in Applied Mathematics from the University of Colorado Boulder. Their research interest is coronal field models, which are used to map the sun's magnetic field and to better understand solar dynamics. So with that, I'm going to stop sharing my screen. I'm gonna allow Dr. Mathews to start his presentation and he'll talk for a little while. We'll take a quick little activity break and then he'll come back on and then we'll do a Q&A. So if you have any questions, feel free to pop them into the Q&A as we go along.
Okay, hi. So thank you so much. I'm very excited. I'm Nat Mathews, and I'm at, like they said, I'm at Goddard, NASA, and I'm a mathematician at NASA, and I work on sun math. So I work on trying to figure out what the sun is doing, what the environment between us and the sun is doing, and how we're being impacted by the sun. So first, I'm going to talk a little bit more about me, how I got into math, how I got into doing math at NASA. And then I'm going to talk about space weather, which is the way that the sun is impacting us. Where does it come from? What does it do to us? Why do we care about it? And how can we forecast it? We want to be able to predict space weather like we predict Earth weather. So I'm going to talk a little bit about that. And then in the second half, I'm going to talk about how the sun makes explosions. It's happening all the time. And these can sort of ripple out. They eject out from the sun. They're called a coronal mass ejection because the corona is our name for the atmosphere of the sun. And I'm going to talk about where they come from and how we can observe them with math. And then I'm going to talk about how we do it on computers to help us figure out what the sun is doing right now. So first, a little bit about me. I'm from Western Massachusetts originally, in the hills of the sort of northern Appalachians. The sky's really dark up there, and I spent a lot of time looking through telescopes. And I went to a performing arts school, so I was majoring in theater. I didn't know I wanted to do math. I knew that I enjoyed math, but my school didn't really offer good math classes. I was biking to a local college, Smith College, to take math there. And then I went off to school to maybe do theater, and I ended up doing math at school. There was a research group that was looking at black hole collisions. So they were simulating black holes on big supercomputers, like server racks in upstate New York. So I worked on that with them for a while. And then I moved to the Rocky Mountains, to Boulder, Colorado, which is right at the foothills of the Rockies, where the Great Plains kind of turn vertical. And I started doing math about the sun there. There was research groups that were looking at parts of the sun and trying to figure out what's going on inside with math, because we can't see it very well. I'm going to talk a lot about that later on. And then I got a job at NASA. So I moved back to the East Coast, and I live in Maryland now. And I'm here at NASA now. So what is space weather? Why do we care about it? There's this thing called the solar wind. The solar wind is blowing off of the sun all the time. It's tiny pieces of the sun, of the atmosphere of the sun, these tiny particles that are constantly billowing off of it. There is a whirlpool that is formed all through our solar system. So in this little video, you can see these little dots. Each one of those dots is one of our planets. And so this is the solar system, and there's this whirlpool of the wind pushing out all the time because the sun at the center is spinning. So as it's spinning, it's billowing out all of these tiny particles, and they make this spiral. And every so often, there's an explosion on the sun. There's one of these coronal mass ejections, CMEs. It's a bunch of particles that are hot and dense and like a mushroom cloud. They shoot off of the surface of the sun and they plow through this wind. They make this wake behind them, like a big boat going through water. And sometimes that hits us. So we want to know when that's going to happen. So the solar wind, this passive solar wind, is happening all the time. But the Earth's magnetic field protects us. The Earth has a magnetic field that all comes out of the North Pole and it all goes into the South Pole of the Earth. And it's sort of squished on the side facing the sun and elongated down on the side facing away from the sun. It's not like a perfect symmetrical apple. And it's because the solar wind is pushing against it all the time. When one of these big CMEs comes through, these big explosions comes through, it can hit this magnetic field and get routed in and interact with our atmosphere. So it's the sun's atmosphere colliding with our atmosphere. And that can make the northern lights, the southern lights, the auroras. There was a big aurora earlier this year in March, and it was because of these huge flares and explosions on the sun. But we're not the only ones in space, right? We have satellites in space also. And they can get hit by these wakes, these explosions pushing through the solar wind too. And so we want to be able to predict that also. And I keep saying solar wind, and it is a wind. You can hear it. We have this probe called Parker that we sent close to the sun, and it sounds like a wind. You can hear it. It's kind of faint. I'm hoping that you guys will be able to hear this. But you can hear the whistle of the wind, and maybe you can hear the ambient background also. I was going to put a recording of a storm, an explosion in here too, but it blew my speakers, so I didn't do that. So this is just the quiet wind. So space weather has real world impacts. We care about this. When you launch satellites during a solar storm, you can lose them. This happened to Starlink a couple years ago. They launched a bunch of satellites while there was a solar storm happening. And the solar storm was pushing on our atmosphere, and it made our atmosphere a little bit denser than it usually is. And the satellites weren't ready for that. And they didn't make it up to the orbit they wanted to reach, and they essentially burned up in our atmosphere. So Starlink doesn't like it when that happens. NASA doesn't like it when that happens. And we want to be able to predict these space weather events, these solar storms, in advance so that we can tell people, don't launch a satellite today. We also have people in space. We have astronauts up there. And for these crewed missions, we want our astronauts to be safe. So if there's a solar storm happening the crew on the ISS, the astronauts on the ISS, go to these specially shielded parts of the space station. There are parts of the space station that we've lined specially, like the crew quarters, to protect them from solar storms, from radiation. And so we want to be, and so right now we tell them, a solar storm is about to happen, get in, but it would be nice to be able to predict for further in advance or how long those storms will be for the astronauts. So how do we do that? How do we forecast space weather? So here is some videos of the storm that happened in March this year that I mentioned earlier. And you can see that there's this active part of the sun, and it's rippling and it's flashing and it explodes. And when it explodes, you can see the atmosphere of the sun in the second video is sort of billowing off. You get this sort of storm of stuff coming off of the sun. It's very hot, very dense, and it's pushing into the solar wind. Here's another video. This one's older, but it's the same thing happening. These explosions coming off of the sun. I like this video because you can see one of them comes right at the camera. We have this explosion coming off the top and then off the side, a little back, and the one hits the camera. These things weigh a lot. They can weigh trillions of kilograms because the sun is huge. So these things are really big too. 1 trillion kilograms is about how much every person on Earth weighs all combined. All the humans on Earth put together weigh about that much. So how do we predict space weather? We wait for one of these things to happen, one of these coronal mass ejections. We can't do anything until one happens. But when a coronal mass ejection happens, we go in and we look at pictures of it from our telescopes and our satellites, from the atmosphere of the sun, and we look at what the surface of the sun was doing, and we fit like an ice cream cone shape to it. We figure out what the shape of it is from trying to look at these projections. And then when we have an idea of the shape, we can figure out how fast it's moving. We look at different frames of the video, and we try to figure out how fast it's moving. And we use the initial shape and the speed, and we put it into these simulations, like the video of the solar wind I showed before, that spiral. That's a simulation we ran here at NASA on a computer. So we put all of this information into these simulations, and we run the simulations, and we try to figure out when this thing is going to arrive. But this is tough because we don't have a lot of views of this thing. We just have the one view from Earth to try to fit this. So we want to be able to do this better. We want to be able to look at this from more angles and figure out what's happening inside of these mass ejections. And we want to be able to do this before it erupts. We want to look at these active regions, like this green active region, and know it's going to erupt before it does. That's the goal. But it's hard to do because you can't go to the sun. It's too hot to send sensors. So how can we measure this? How can we measure these things when all we have is pictures from far away? That's the big problem we're trying to solve at NASA. You can't take sensors into the sun. We flew Parker Solar Probe, the thing we listened to earlier. We flew that close to the sun, but it's not close enough to measure these things. It's out in the wind. And we only have one angle. We would love to build, like a CAT scan around the sun to sort of see inside. When you go to the hospital and you get into an MRI machine, you get into a CT machine, it looks at you from every angle and it sort of shoots X-rays through you or looks at magnetic fields through you, and it tries to figure out what's happening inside. We'd like to do that for the sun, but we can't build all the way around the sun We can't surround it to look in from every angle. We could maybe break that apart into a couple of telescopes, and we're talking about doing that. But we don't have those in space now, so we can't do this right now. All we have, for the most part, is one angle from where the Earth is to look at the sun. We have a couple of telescopes out in space, but mostly they're in line with the Earth. Sometimes they rotate around, but not all the time. So it's hard to count on that. So we are going to do a little breakout activity where we're going to talk about, we're going to look at how this impacts what we can learn about objects when we can only see them from one angle and we can kind of see through everything, and what we can reconstruct about what's happening in situations like that. And then we'll regroup and we'll talk about how to do this with more angles and do this with math.
Okay, great. All right, so here's our little activity. So what you're looking at is an image of a bag scan from the Transportation Security. So, when you go to the airport and they send your bag through that machine, this is something similar to what they might be seeing on their screen as your bag goes through. So just take a few minutes, and I want you to name as many objects as you can. So I've opened up the chat for you. So if you want to drop your ideas as you get them into the chat, that would be wonderful. And then just think about, like, are there any objects that are particularly tough to identify, and maybe why that is. So we'll give us about 5 minutes or so here to do that. All right, so we've got a couple of ideas populating the chat right now. So we've got maybe what might be like an iPad, perhaps. Definitely. Could be like a phone, maybe. We've also got maybe a perfume bottle. Okay. I see a pair of glasses. It's kind of hard to tell though if they're like reading glasses or if they're sunglasses. There's a bunch of objects kind of on the bottom there that are really hard to tell what they are. Okay, yeah, could be lotion maybe. Or maybe like one of those little pots of like lip balm. I do see what looks maybe like a pen. But there's definitely some stuff on the bottom there that I'm not sure what it is. So fortunately, we happen to have another view of this, so I'm going to switch to that. So here's a different angle of that same bag. So now look at this and look at what you initially wrote. Are there any objects that are now much clearer that you're like, yes, I definitely got that? What objects are you still unsure about? Is there anything that you see here that you didn't see in that initial picture? So go ahead and drop your thoughts into the chat there. Yeah, there's a key, right? And you could almost maybe see the key before, but now we can see that there's like a heart-shaped keychain on it. So that's definitely much clearer. And we've got maybe what might be like lipstick. We've got some earbuds, right? Yeah, headphones, exactly. Didn't see those at all before. And now we've also have like maybe what might be a notebook or like a journal. We could kind of see the outline before, but it was really hard to tell what it was. So definitely the ability to be able to see things from a different angle gives us a lot more information about what it is that we are looking at. All right, so with that, I am going to stop sharing. I'm going to transfer it over to Dr. Mathews to let him continue to inform us about his research. All right.
There we go. Hello, thank you. So how does the sun make an explosion? We're going to talk about how we're going to link these explosions to the kinds of observations that we just made. But first, I want to take a brief tangent and talk about where these things come from. So there's a magnetic field in the sun. Like the Earth has a magnetic field, the sun has a magnetic field. But it doesn't all come out of the North Pole and all go into the South Pole like the Earth's does. It's all over the place. And a lot of the time, the way that happens is it has this sort of magnet under the surface that I think of like one of these U magnets. It's got a North Pole and a South Pole, and the magnetic field just connects them. But the magnetic field is bulging out of the sun and into the atmosphere, into the corona. And sometimes it's straight like this, but a lot of the time it's twisted up. It's bunched up like a slinky. And we can't see it. We can't see this magnetic field at all. All we can see is the stuff, the hot, dense atmosphere that falls into the magnetic field and flows along it. So you can think of the magnetic field coming out of the sun like the bed of a river. And the plasma, the hot, dense particles in the atmosphere are like the water in that river. And that's what we see. That's the stuff that glows, that makes light that's observable. So we have to use that visible signature to try to figure out where the magnetic field is. Remember, this field was twisted, but does it look twisted or does it just look wavy? This is hard. The magnetic field gets more and more twisted over time. It builds up energy and it's sort of bound together. It's like taking those two feet of the slinky and twisting them. And it gets tighter and tighter and tighter until it breaks. It pops. And this little island that's been separated from the main arc gets launched into space. That's the explosion. That's the solar storm. That's what we're trying to predict. So we have to see these magnetic fields and how bunched up they are to know when they're going to break, when they're going to launch into space. But we don't have that second angle like we had for that bag in the activity. So how can we figure out what all the stuff is at the bottom? Because perspective can fool us, right? I was just saying earlier, does this look twisted or does it just look wavy? It's hard to tell. If it is twisted, How twisted is it? Remember, that's the thing that matters the most. That's the thing that's going to drive when this explodes. And it's hard to tell from Earth if you can't see the field itself. We use math. We solve this problem with math. That's why I'm here at NASA. We have a bunch of equations, big, complicated equations that tell us how physics works on the sun. You can write them down with a pen and paper. They're little equalities that relate the magnetic field and the plasma, and that we know have to be true for physics. And we can use computers to solve these equations. They're huge and complicated, and they're hard to solve with a pen and paper, but you can solve them on computers. And when we do those solutions, that gives us a model of the magnetic field that the sun could have. It's self-consistent. It's a kind of field that could exist on the sun. This is what's called a forward model, where you say, well, I know what the equations are, and I know some, and I can build the kind of thing that can happen on the sun. How do we do this? How does this kind of math happen? Well, we start with a guess. If we know what the gas is doing on the sun, we could guess at what the magnetic field would have to be. And that guess won't be right. It won't be right. But we can figure out how wrong it is. We can plug that guess into those equations, and that equality, the equal sign in the equation, won't work. But we can rearrange the equation and say, okay, well, what's left over? How can we make this equal sign work? And we can sort of rearrange and subtract from both sides and do what we have to do to update our guess to make it less wrong. And we just keep doing that. We iterate that process. And because it's on a big computer, we can do it really fast. And that way we can change from this initial guess, which is not right. It does not look like it's going to match the plasma that we have, the force, the pressure, the gases that we have. And we sort of nudge it until it looks more like a magnetic field that will match, that is consistent, that's realistic, that could exist on the sun. So that's a forward model. But that's not what we're doing, because we don't care just about the kinds of things that could exist on the sun. We want to know what does exist on the sun. We want to know what the magnetic field on the sun is doing right now. And so we do this. We can't remember, we can't look at the sun from a bunch of angles, but what we can do is make a bunch of different simulations of the kinds of things the sun can have, a bunch of different models, mathematical models of the kinds of things the sun can have, and look at each of them through a computer telescope. We pretend the computer is a telescope, and we say, what would this look like if this is what the sun was doing? And we compare those pictures to the real sun. So what does this mean? Let's root this a little bit. So I like to think of the computer model like this. This is my drawing of a computer model. And we have a knob that we can tune. And every time we tune this knob, we get a different simulation. Here, the knob is how high up this magnetic field is above the surface of the sun. And for each one of these simulations that we've set, we can figure out what the sun would look like if this was on it. Here, these pictures are a kind of observation you can get from the sun in what's called polarized light. So it's when all of the light waves are sort of oriented the same way. If you go to a 3D movie, you'll notice that they give you sunglasses, right? And the sunglasses just let through some flavors of light, some orientations of light. And so that's what we're doing here. We're just letting through some orientations of light, because it turns out that the way 3D movies work and the way the sun works is kind of the same. When these light rays go through a magnetic field, they turn slightly, and we can detect that. These are called lagomorphs, which means a rabbit shape, I think because they look like a little bunny rabbit. But we can make these observations, these pictures, for the different magnetic fields. So if this was on the sun, that's the observation we'd get. If this was on the sun, that's the observation we'd get. And we have a real observation from the real sun, too. We have a telescope in space. It looked at the sun with this kind of oriented, polarized light. And this is what it saw, which doesn't really look like any of our simulations, but it looks maybe more like one of them than the other. And we can keep tuning this knob. And every time we tune it, we say, okay, well, how different does this look? How different does this look? Let's quantify it. We'll add up all those differences. And we make a plot, we make a graph. We make a graph that says for every place we tuned that knob to on our computer model, how different were the two pictures? And then we look for the low point of that graph. We use math and we find the low point of that graph, and we say that place where that knob got tuned is where we think the right field is. So we just minimize, we find the low point of the graph, and that gives us a field that we think is the field that really is happening on the sun. So that's about it. We have space weather. Space weather comes from the sun, right? We have these fields, these active parts of the sun that are bubbling and boiling, and they explode, and they send these walls, these wakes into our solar wind, which can crash into telescopes. They can crash into the Earth. They impact our communications. They can take out, telephone lines. And we want to be able to predict these. And to predict them, we need to have a good view of what's happening on the sun right now. But that's hard because the atmosphere of the sun is translucent, and we can only see it from one angle. So it's hard to tell where along our line of sight these structures are. It's hard to tell how twisted they are. But we use math and computer models together, and we make observations on our computer of the sun, and we compare them to the observations we took of our sun, and we figure out what the most likely structures are. And that helps us update our predictions for space weather. That's about it. There's a bunch of people here at NASA who help me with this stuff. And there's people all over the rest of the country who are working on this stuff. And it's a big effort towards sort of protecting the stuff we have in space and the people we have in space. Thanks.
Okay, wonderful. Thank you. All right, so we're going to head over to the Q&A and see what kind of questions we have here. So the first question, you mentioned how the solar wind or these solar flares, how it impacts like astronauts in the space station, and how it affects things in our like our satellites and stuff like that. Is there any, like, for people on Earth, is there any, can we feel it? Does it have any implications for like us humans here?
Yeah, so you can see it when a bunch of plasma from the sun, one of these storms, hits the Earth's magnetic field. The tiny particles hit the magnetic field and they boil around into our atmosphere, and they collide with our atmosphere, and they release a bunch of energy. And that's what the aurora is. So if you ever see on the news, the aurora is pushing south, or there's a really strong aurora borealis, That's because of these solar storms. If they're really powerful, they can impact telecommunications. They can make it harder to access the internet while they're happening, or radio, because they're balancing around in the ionosphere of the Earth. There was a huge one about 200 years ago in the 1850s, and it disabled every telegraph line on Earth. There were telegraph operators who reported being able to send and receive telegraph messages with Europe when their telegraph in America wasn't plugged into anything. So that can happen. And if that happened today, imagine what it would do to the internet. But it doesn't impact like our biology. There's no direct, the magnetic field of the Earth protects us. So this radiation isn't sort of making it down to the ground.
All right, and that kind of dovetails into one of these other questions you mentioned. This was like back in 1850. How long have we been, making these predictions, gathering data about the sun? Like, how does that go back?
So we've been measuring, so there's this thing called the solar cycle, which is 11 years long. And it is, the sun gets more and less active over time. It has sort of periods where it explodes a lot, and then periods where it's very quiet and sleeping. And it lasts 11 years. And we're on what's called solar cycle 25. So we've been measuring this for a while now, like almost 300 years. And so, but for the most part, most of that was sort of looking at the surface, because if the sun has these active regions or sunspots, they're a little bit dimmer than the rest of the sun around them, because they're very slightly cooler, because they're denser. So we've been tracking those across the surface for a long time, because people would build big windows in their roofs with lenses, and they would project the sun down onto the floor. So they would project this image of the sun onto the floor, and they would trace it, and they would draw out where the sunspots were. And we've been doing that for hundreds of years. But stuff like this, of looking at the atmosphere of the sun all the time and trying to track these mass ejections as they move through our solar wind, we've been doing this kind of stuff for more like 20 or 40 years.
So do you see this as a growing area in terms of like job opportunities for people who might be studying this type of thing?
Absolutely. We care a lot about the sun for a few reasons. One, we have to live with it all the time. And as we're doing more stuff in space, this is mattering more and more. We're sending astronauts back to the moon, the Artemis mission, and we have to have a good handle on space weather prediction to do that. Because we need to be able to protect these astronauts as they go to the moon. And so better prediction for space weather is really important. And we're launching more missions to look at the sun from more angles. There's a mission called Sunrise, which is going to be sort of positioned off to the leading edge of the sun as it rotates. So we'll be able to see it. Sunset. But also, like, the sun is a star, and it's the star that's closest to us. That's the easiest for us to see. It's the easiest for us to measure. So looking through Hubble at all of these other stars, and as we're looking at exoplanets, and we're trying to detect exoplanets around distant stars, we can use our sun as a Rosetta Stone for how stars impact the planets and the system around them. And so we're doing that more and more too.
All right, another question here. So you talked about, these coronal mass ejections. Is there, and I know you're still tracking this, but like how frequently, do we have like an average on like how frequently these things occur?
So coronal mass, so remember, the Earth's pretty small. In space, the Earth is very small. So even if coronal mass ejections happened pretty frequently, most of them wouldn't hit us. A lot of them would miss. And they don't happen that frequently. When the sun is active, we can have, 30 or 50 a year, like every few days we might have one, every week we might have one. And they kind of tend to come in spurts too. You remember this? Here, I'm going to go back in my presentation very quickly. Here in this video, we can see that there's a bunch sort of happening all at once. This video takes place over the course of one day. So you can see that they're sort of billowing off. Or in this one, there's sort of 3 back to back. So they can come to grouped together, but there will be like a week where nothing happens. And this is during the most active part of the solar cycle. Remember, it's this 11-year-long cycle. When the sun is quiet and sleeping, there might be like 1 or 2 in a year.
All right. So another question here, do solar flares impact climate change?
That's a good question. And we don't really know. We think they probably do because there's a lot of energy in them, but it's hard to tell. What we have been doing is looking at historical flares. If I said, we wanted to study a flare that happened 100,000 years ago to be able to understand the difference between how active the sun was then versus now and how that might be impacting climate change. How do we do that? We can. What we do is we go to the Arctic and we dig up these ice cores, and we use these ice cores to look at historical levels of weird ions in the atmosphere. And we use those to figure out we figure they must have come from the sun. But if there is an extent to which the sun impacts the Earth's climate in this way, that solar storms impact the Earth's climate, it's probably very small. It's not, a main driver of, for example, the climate change we're seeing today.
All right. Question about the equations when you're working on those, the simulation, and you said you can sort of nudge it to try to get it to match up, and you're fine tuning it with the knob. Like, how long does that process take to be able to sort of match up the simulation with what you're seeing? And
yeah, so it depends a lot. Because there's this thing called the curse of dimensionality that we talk about on computer simulations. But the picture that I drew with one knob to twist to find the best fit, you can do that very fast. But in practice, you don't have one knob. You have like 100 knobs or 500 knobs. And trying to find the sweet spot where they're all at the right place, that can take a long time. That can take weeks. And clearly, we don't have weeks if we're trying to do this kind of prediction in real time. That's why it's active science. We're trying to figure out better ways to do this. And so that's the inverse problem point from the forward modeling point, where you have this equation and we're trying to solve it to build a magnetic field. With good computers these days, you can do that in a few hours to a few days, depending on how accurate you want your model to be. Because the real world is what we call in math continuous. You can have a measurement wherever you want. However fine a measurement you want, you can put a probe there and sense the magnetic field. But computers are what we call discrete. They're at given points, you have a magnetic field, and you only define the magnetic field at those places. And so we're using this sort of discrete, distinct points, and we're pretending that it's like real life, that it's all smooth. And so you want to put those things as close together as possible, but that makes the simulation take longer to do. So it's a sweet spot you have to find and balance, and it depends on how strong the computer is.
all right. So another question here about so we're talking about predicting it so that we can, take shelter or, not launch satellites. Is there any way to like to build a shield or something that makes like that protects Earth from solar flares?
So the Earth has a really good shield already. The magnetic field that we have protects us from this kind of stuff. The problem comes when you're up high past our magnetic field, or where our magnetic field is a little thinner or isn't as strong. So the ISS astronauts have to deal with this in a way that we don't. And we do shield them, and there's parts of the ISS that are built to protect them. We have these boxes about this big, and we've lined parts of the ISS with them because they protect from solar radiation. We can't build a big shield between us and the sun in space because we need the sun. The ambient light coming from the sun is very important for life on Earth. So we don't want to block all of that out.
Okay. All right. And I think another question here. So I know solar weather is very complex, and there's people at NASA working on different heliophysics topics. But is there like any sort of like citizen science projects or any way that the average citizen can help with this type of research?
Yeah. So there's a lot of places to get involved. This is the heliophysics big year, they've been calling it, with the eclipses and stuff like that. And there is a project called Aurorasaurus, where we're asking citizens to help us map the auroras, which come from space weather from the sun. There's a project that had people listening to data from Parker Solar Probe that the sonified stuff that I'm not sure if you guys can hear, and listening for weird bits like whistles or crashes as solar storms go through, and stuff like that. So there's citizen science around this kind of data because the ear is better at seeing this stuff than a lot of other tools. There's citizen science projects around radio astronomy, and the radio telescopes looking at the sun. And there's resources on the NASA webpage about all of this stuff.
Okay, great. All right, so last question here. Do you have any advice for students who might be interested in pursuing a career in science or mathematics or sort of anywhere in this space?
Yeah, I think there's I have two big pieces of advice. One is that you still have to, if what you want to do is science or math or computer science or things like this, your other classes are still really important. My job is partly doing math about the sun, but it's largely telling other people, like scientists, about the math about the sun that I've been doing and helping them with their math about the sun. So communication and writing is really important. When we make results, we publish them and you put them in a journal, and then you write about it, you put it in a journal, and then other people read about it. So they're reading the stuff. So all of that stuff is important. The other thing that I would say is that math is more than just equations. It's a way of thinking about stuff. Science is a way of thinking about stuff. And so just having the curiosity and like the desire to bend your brain to think about things in a new way or from a new perspective can be really important. And trying to like look at things from different angles and sort of get a surround on the topic. And that kind of thinking about things in different ways with different perspectives is really important in science and math. And that kind of logical thought process is something that takes practice. Like I said, I went to a performing arts school, so I was like biking to colleges to take math classes when I was in high school because I didn't have the resources at my high school to do that stuff. So sometimes you have to sort of go out and find this learning. It's not just going to show up.
All right, I love that. Thank you so much. All right, so with that, we're just about out of time here, so I'm going to wrap it up with a huge thank you to Dr. Mathews for joining us today. And I think you did a fabulous job of really breaking that down. It's a very complex topic into something that we could all kind of understand. So thank you for that. And for our participants today, I'm going to put our survey link in the chat. So if you would please fill that out and give us a little bit of feedback about what you thought about today's presentation. And I'll also give a plug for our next presentation, which is going to be this time next Thursday. That's going to be all about the Earth's magnetic shield and how it protects us from different hazards. So I'll put the registration link for that one in the link as well. All right, and thanks so much for everyone for joining us. Any parting words, Dr. Mathews?
No, I don't think so. Thank you so much. This was great.
Okay, wonderful. All right, thank you everyone for joining us today. We hope to see you next time.